for an NCT 2018, and it's tutorial number 3, Introduction to the Bitcoin by Dr. Saravanan Vijayakumaran IIT Bombay. So Dr. Saravanan received a BTech from an IIT Guwahati in 2001 and a PhD from the University of Florida, Gainesville in 2007. After a brief stint at the Microsoft in Redmond, he joined the Department of Electrical Engineering at the IIT Bombay in 2009, where he is currently an associate. And so his research interests are in error correcting cores and signal processing for communications, and he became interested in the cryptocurrency technologies after attending the Scaling Bitcoin workshop in 2016. So now he's writing a book on the Bitcoin, and the first shot is available in his website. I think it's here. Yeah, it's already shown. And also he received the Departmental Award for Excellence of Teaching at the IIT Bombay in 2017. So Dr. Saravanan.
Thank you. Oh, thank you. So can you hear me in the back? That's fine. Yeah. So thank you for the invitation. It's good to be back in Hyderabad. I'm from Hyderabad. I stayed here for 17 years before going for my undergraduate and graduate studies. So I'll be giving a brief introduction to Bitcoin. So what is Bitcoin? It's a cryptocurrency, which means that storing and transferring this currency involves cryptography. It also refers to some open source software which you can download and run on your computer. Bitcoin also refers to a decentralized network, so something like this. So there is no central coordinator. Every node is equivalent to every other node. So once we have a decentralized network, there are some challenges with implementing a currency using a decentralized network. So what are the challenges? First of all, counterfeiting. When you have a central authority which issues a currency, the central authority like the RBI will define identifying characteristics of authentic currency. So when is a currency note authentic? And if it doesn't have those identifying characteristics, it's considered a fake currency note. But when you have a decentralized network, who defines what is authentic and what is fake? Also, what are the rules for creating the currency? When you have a central authority, then the amount of currency which will be printed will be decided by the central authority. But when you have a decentralized network, who decides how much to print and at what rate should it be printed? And also there is this problem of double spending, which is unique to digital currencies. So digital currencies exist as a string of bits which can be copied perfectly. Consider this situation where Alice pays Bob's and digicoins for pizza. Digicoin is some digital currency. I'm not saying bitcoins here because Bitcoin solves this double spending problem. So let's assume that you create a digital currency. Alice pays Bob for n digicoins for some pizza. But Alice can then make perfect copy of those n digicoins and pay Carol for some books. So this is the double spending problem. That is, the same digital currency unit is being used twice. In fiat currency, like rupees or dollars, if I have a currency note, I can't double spend it. Once I pay somebody with that currency note, I give the pizza delivery guy the currency note, I can't take it back from him and pay somebody else. Even when we use digital transactions for spending fiat, like if I use a credit card or if I use a bank account, if my bank account has only 1,000 rupees, if I spend that 1,000 rupees, if I try to spend again, the bank will say that insufficient balance. So when you have a central authority, it's easy to solve this double spending problem. But how do we do that without a central coordinator? And Bitcoin solves this problem, the double spending problem. And it also solves the other two issues of counterfeiting and currency creation rules. But let's look at the double spending problem first. So how to solve the double spending problem without a central coordinator? So double spending is familiar to academics. Double spending is just like you submit the same paper to 2 conferences. That's like a double spending. A paper you can make a perfect copy of it, just send it to 2 conferences. That's like double spending. And the one possible solution is that the reviewers, when they receive a paper, they may just Google for the contents of the paper, and if they see that that paper has been published somewhere else, then they'll say that, hey, this paper is already been submitted to a conference. But this solution, where the reviewers search online, does not work if the 2 conferences are accepting papers at the same time. So there is no digital, there's no place where Google will give you results. And also it will not work if the conference proceedings are not published. Many conferences may not publish their proceedings. So even if a reviewer Googles for the paper, he may not find it. So a better solution would be that if we can maintain a single public database, which anybody can search, which has all submissions to all papers. Then reviewers can search through this public database and check if somebody is trying to double spend their paper, try to get it published in 2 avenues. So this is the basic idea of the blockchain. The blockchain in the context of Bitcoin is just a public database for storing transactions. So it will be used to solve the double spending problem, because if every transaction is stored in a public database, so when somebody tries to double spend Bitcoins, the person receiving payment will just check if those Bitcoins have already been spent. So that is what the blockchain is. This term means different things in some other technologies, enterprise databases, enterprise blockchains. They may store many other things, but in Bitcoin, it just stores transactions. By that I mean transfer of Bitcoins from one entity to another entity. So how does the blockchain look like? It's just a linear list of blocks. So each block will have a block header and then a list of transactions. And each block has a height. So the first block was called the Genesis block. It was created in 2009. It has height 0. And then the next block has height 1 and so on. So now more than 500,000 blocks have been created. But you may look at this and think, okay, I see these blocks, but what is a chain? Why is it called a blockchain? So to understand that, we have to look more carefully at this block header. So this is how the block header looks like. It is an 80-byte block header. So you see that I've named these fields. So there are 6 fields, and the bytes, how many bytes each field occupies. So you have 4, and this is 64, and then plus 16, so it's 80. So these variable names are actually C++ variable names. So Bitcoin does not have a specification document. So the creator of Bitcoin, he wrote the initial code in C++. It's still, so there is a client or a software, the Bitcoin software called the Bitcoin core, which is written in C++. So these are actually C++ variable names. Now there are many implementations, but the first implementation, which is still being used today, it is considered the reference implementation. So any other implementation needs to maintain bug-to-bug compatibility with that implementation. So there is no specification doc, because it's a protocol. So typically protocols have a specification document. So there is no specification document. There's just an implementation in C++. It's called Bitcoin core, and that everybody else needs to follow that implementation. So these are variable names, C++ variable names. So they have the naming convention is that if your variable contains an integer, there is a little n at the beginning. So the first and these 3 are integers. And if the variable name starts with hash, it contains the output of a hash function. So we'll see what a hash function is. This is just the output of a hash function. Okay, so where is the chain? So the thing is that if you look at the previous block header, 80 bytes, you compute something called the double SHA-256 hash of these 80 bytes, and the result is 32 bytes, which is entered into the hash previous block, the hash of the previous block in this field of the current block. So that is where the chaining comes from. So the current block depends on the previous block through this hash. So what is this SHA-256? It is a cryptographic hash function. SHA stands for secure hash algorithm, and 256 is it is 256-bit output. So 32 bytes is 256 bits. So this was a NSA designed cryptographic hash function, by NSA I mean National Security Agency of the US. So what are these cryptographic hash functions? So why is it that you have this chaining using this cryptographic hash functions? So let's look at some properties. So first of all, the input can be of variable length. The output is always a fixed length. So SHA-256 has 256 bits. Then SHA-512 will have 512 bits and so on. So the output is a fixed length bit string. It is a one-way function in the sense that it's easy to compute in the forward direction but difficult to invert. So what I mean by that is that if I give you the output h of x, where h is a cryptographic hash function, it's computationally infeasible to find x. So if I just tell you that this 256 bits correspond to the output for some input, it's very difficult without doing an exponential number of operations to find that x. So it's a one-way function. You can compute it easily in the forward direction. For any x you can compute h of x, but if I give you some output y and say what is the x corresponding to this output, it's very difficult. It's collision resistant, which by that I mean that it's difficult to find two distinct outputs which have the same output. Sorry, two distinct inputs which have the same output. So it's computationally infeasible to find two distinct inputs x and y such that the hash function outputs are the same. So it's resistant to collisions, and it behaves like a pseudo-random function. So it is, by pseudo-random function, it looks like the output is uniformly random. So if you look at this picture where I have these bins, so the output is 256 bits. So I have bins indexed starting from 0 to 2 raised to 256 minus 1. There are 2 raised to 256 bins. If I give some inputs to this SHA-256 function, it will appear as if the corresponding outputs, let's say y1 is the output corresponding to x1, y2 is the output corresponding to x2, y3 is the output corresponding to x3. It will appear as if these outputs are uniformly distributed across all these bins. Okay. So let's look at a short demo. Any questions so far before I show some demo? Any questions? No. So I've written a small Python code which computes the SHA-256 hash function. So I have okay, this does not look good. Okay, that's better. So I have two columns here. This is the input to the SHA-256 function. So I've calculated the output for 10 possible inputs. So NCC 0, NCC 1, NCC 2 up to NCC 9, and this is the corresponding SHA-256 output. This is in hexadecimal. So each character is in base 16. So there are 256 divided by 4. That's 64 characters there. You can see that, look at NCC 0 and NCC 1, it differs only in this last integer, but the outputs look completely different. Similarly, for different inputs, it appears as if the output was randomly chosen from any of those 2 raised to 256 outputs. So that is what I mean by a cryptographic hash function being pseudo-random. It is computationally indistinguishable from a completely random function. That is a function which uniformly chooses outputs from this 2 raised to 256 possibilities. Any questions about this? So the thing is that this SHA-256, it can take arbitrarily long. Okay, there is a bound, but a very large bound on the length of the input. So, but it can definitely take inputs which are more than 256 bits long. Yeah. No, it's not dependent on, it's not a time dependent thing. So like for example, I have h of, if I just do this NCC 0 again, I get the same thing. So it is, like if you see this, I just calculated NCC 0 again. H is, I've stored that SHA-256 there. So it just gives me the same thing. So it's not dependent on any time. No, so far SHA-256 has not been, so in the sense that what does it mean to be inverted? In the sense that Okay, if I calculate some forward values, then given this, I know that that is one possible inversion. But note that the input can be more than 256 bits long, so it's a many-to-one function. So collisions do exist, but it is just computationally difficult to find them. So the idea is that if you look at this picture, 2 raised to 256 is a very large number. It's more than the number of atoms in the universe and so on. So if I calculate some the output corresponding to some inputs, it will fall in this very large space of bins. So it's very difficult for me to find two inputs which will fall in the same bin. This is an unimaginably large number. It's like really large. 2 raised to 256 is very big, and that is the reason hash functions work. So the space is so large that we may calculate the input for many, how many ever times we can do in our lifetime. You still find it difficult to find two inputs which collide in the same, which will fall in the same bin. SHA-1, which was a previous version of the secure hash algorithm, Google and some other researchers have found collisions. So it is not recommended to use SHA-1, which is a weaker hash function. SHA-256, still nobody has been able to find collisions. Okay. Okay, so any questions about this? So this the script is not very mysterious. It is okay. So this there's a library called hashlib in Python, and hashlib has a SHA-256 built-in function. And here I'm just defining something called an anonymous function. Lambda x is the input, and the output is SHA-256 of x, and I want the output to be formatted in hex format. So that's why it's hex digest thing. And for 10, I'm going to run a loop for 10 times for I in range n, and I'm just concatenating the integer, the string corresponding to the integer to NCC, and I'm printing x, which is the NCC 0, NCC 1, and the output of the hash function. So it's just a simple, yeah. It's computationally for any polynomial time distinguisher. So distinguisher is, so suppose you think of an adversary who can do only polynomial time operations. Then the probability that he'll be able to distinguish between the pseudo-random function and a completely random function in the sense that an ideal model which is uniformly picks say that again. So it is like usually these definitions are done in terms of a game. So suppose I have a distinguisher D, and he is a distinguisher. So he is restricted to be probabilistic polynomial time. So he can do random things, but so he is given either the pseudo-random function, let's say SHA-256, or a completely random function which maps some strings, or no, it should not be a mapping. So it is a idealistic thing of F. So I just uniformly choose, let's say I have a random function which for each input the output was uniformly chosen from 0, 1 raised to 256. So if this distinguisher is given one of these inputs, so the probability that he'll be, so distinguisher is going to, the domain is going to be either SHA-256 or this random function. And the range is going to be, he'll say 0 or 1. That he says what you gave me is either the SHA or the random function. So the probability that he'll output the distinguisher when given SHA the input, the probability that he'll output 1 is indistinguishable, is negligible. So that is like it's unnecessarily formal, but that is what I mean by it is pseudo-random. A pseudo-random function is that it is computationally indistinguishable from a completely random function. Completely random function is that you consider a set of all functions and you pick f is uniformly chosen from func n. So, but the key thing is that polynomial time, because if I have an adversary who can compute an exponential number of, can do an exponential number of computations, then he should be able to find a collision, because he's or he can also invert by just he just keep trying. Suppose I give you some y3, he'll just keep trying inputs until he finds a input which maps to y3, but he'll end up doing an exponential number of operations. Okay, so this is a cryptographic hash function, and these play a crucial role. They're a primitive in cryptography, so they appear all the time. You are probably using it on a day-to-day basis. Whenever you connect to your bank website or any website using secure HTTPS, there will be a digital signature involved. And the digital signature uses hash functions to create that digital signature. We'll see that in the context of Bitcoin also. So let's say we have this. So why are we looking at this? Because I said that the chain, that blockchain, was that the hash of the previous block header was being inserted into the current block. So why is that? So there is so you want dependence between the blocks, but this hash function also plays a role in Bitcoin mining. So what is this Bitcoin mining? So to motivate that, think of the blockchain as a public database. And when you have public databases where anybody can write to it, you'll have the problem of spam. So you want to prevent this spam, and all of you do own a public database where anybody can add entries, which is your email inbox, right? Anybody can just send you an email. They know your email address, they'll send spam to you. So how do you prevent spam? Okay, people use spam filters and maybe machine learning to figure out what is spam and not spam. But in 1997, there was a scheme which was proposed called Hashcash, which is based on these hash functions. This person called Adam Back had proposed it. Some researchers in Israel also had proposed it before, but Hashcash is used, or in the Bitcoin mining uses the idea behind Hashcash. So what is Hashcash? You have this protocol where a client wants to send an email to a server. So you have an email client, he wants to send an email to a server. The client and server will agree upon a cryptographic hash function. They will say, okay, let's use SHA-256. You'll fix that. Then the server sends a challenge C to the client, and the client is supposed to respond with a response X. So this double vertical bar is string concatenation. So the challenge C is there, and then the challenge is concatenated with the response and sent back. Now the requirement is that the hash of C concatenated with X should begin with K zeros. Okay. So to understand what that means, so this let's consider a hash function which has only three hash function with 3 bits, just for argument's sake. So suppose I have 8 bins. So the bin indices will be 0, 0, 1, 0, 1, 0, 0, 1, 4. So these are the bin indices in binary. So suppose K is 1 here. I want to find a string such that the hash function output begins with K zeros, which means that I need the bins, they're supposed to be these bins. So all these bin indices or the outputs of the hash function, they start with 1 0 when k is 1. So if you consider hash function as a pseudo-random function, then if I calculate the output for any input, with probability half it will fall in this part. Okay. Now if I specify k equals 2, what begins with 2 zeros? So there is only these guys. So if I calculate the output of the hash function, then with probability 1/4, 2 out of 8, it will fall in these first 2 bins. So as k increases, the problem becomes harder because the probability of an output starting with k zeros decreases as k increases. So to be precise, if you are since H has pseudo-random outputs, the probability of success in a single trial is 1/2 raised to k. So if I start with k zeros, k are fixed. The remaining n minus k bits can be anything. So there are 2 raised to n minus k possibilities for the remaining bits. The total number of possibilities is 2 raised to n, where n is the length of the hash function output. So it's 1/2 raised to k. So as k increases, the problem becomes harder. Okay. So the server, and how does this prevent spam? So this before a client can send an email to the server, he has to solve a hard problem. So if k is like 32, then he has to, something succeeds with probability 1/2 raised to 32 in a single trial. On the average, you need 2 raised to 32 trials before you can find such an output. So did I have the, and this x corresponding to c, but c was a challenge and the x is called the proof of work. So the client is proving to the server that he has done some work. So this is what is called proof of work in this Bitcoin, in the context of Bitcoin. So I'll show you a small demo. So I've written a script called hashcash, and let me load it in Python. So this hashcash so the function is going to take 3 inputs. One is the challenge and the number of trials and the number of zeros. Number of trials is that we know that in a single trial the probability is 1/2 raised to k, so we may need to do more than one trial to succeed in finding an input which starts with whose hash starts with k zeros. So let's try this. So let's say hashcash ncc, and let me try 10 times, and I wanted to start with 4 zeros. Then it says, okay, it's not enough because when k is 4, number of trials is 4. I need the probability of success 1/2 raised to 4, 1/16. So I probably need more trials. So I need at least 16 trials on the average. So let's make this 16. See what happens. It didn't work because it's not deterministically 16. Can be slightly more. Let's say 25. Okay, after 22 trials, I was able to find a response or the X. So NCC was a challenge. 22 is the X I'm appending. So I said the hash starts with 4 zeros. So again you have hexadecimal outputs. So 4 binary zeros is 1 hexadecimal 0. So it's starting with 0. Now if I increase this number of zeros to be higher, let's consider multiples of 4 because we have hexadecimal output. So let's consider 8. Again it says not enough trials because 1/2 raised to 8 is 256. So 25 trials won't suffice. So let's try 256. Let's see. Okay, it worked out. After 121 trials, I was able to find the response such that the hash of NCC 121 is starting with 2 zeros. It's 8 binary zeros, so it is 2 hexadecimal zeros. And once the server gets this challenge concatenated with say that again? Yeah, it will be the same. So you mean like NCC 121? like this. So the hash function is a deterministic function. It is pseudo-random. By that I mean it is a deterministic function. The pseudo part is because it is deterministic yet looks like a random function. So it's not going to change its output for a given input. It will be always fixed. How is that? No, why? So first of all, these trials are being run at the client side because the server sends NCC. The client tries NCC 0, NCC 1. It keeps on trying. No, I computed it again. H is the SHA-2 of physics. So I computed again. I got the same thing. So it is like like we saw in the. No, it's pseudo-random. Why will it work? 122. It doesn't start with. NCC 122. Oh yeah, I did return the same thing. You're right. So his the comment was that the number of trials he tried was 256. But as soon as the client, so if instead of this I change it to 122, it will work. So you can just check that. Not a big deal. It works. So the client will not anyway run more than the number of trials required. So after every trial, it will check that is it start with 8 zeros, then it will stop. It will not do that, but as a demo, I just have a large number because I don't know what it will be. Yeah, the hash is known at the client. Then the client will respond with NCC this 122, and the server needs to calculate only one hash, while the client needed to calculate 122 hashes, 0 to 121. So server needs to calculate only one hash. So when the response comes back from the client, the server will just calculate the hash of the response, that is challenge concatenated with the response, and check that, sorry, this one, challenge concatenated with the response, check that it starts with 8 zeros. Then it will say, okay, now you can, I'll accept the email you're sending me. Submit. So the protocol was server. That is only for demo. You can concatenate anything, but I just wanted a demo. Yeah, so the response you can say, yeah. So this, yeah, it can be anything. So just like a demo for demo, so I wanted something I can iterate over quickly. And since it's pseudo-random, concatenating a number or a string doesn't give any advantage because anyway you don't know what the output is going to be. Say that again. So why does it need to be secret? Yeah. Yeah. No, but the server only wants something to begin with k zeros, so it does not specify what needs to be added. So there is no advantage in specifying a random string because you're saying that iterating over a random string is difficult. Why is that? Yeah, but I cannot force the client to say that iterate over a string. How can I do that? So we both agree on a hash function, and we say that the server only says you send me any input. I don't care how you generated that. You just send me some input. It should always begin with the challenge I sent you, because if this is not there, then the client can just pre-compute and spam me. This is to prevent pre-computing. The challenge is not known to the client until he connects to the server and says, I want to send you an email. Then the server will generate a unique challenge so that people don't pre-compute and spam. Unique challenge will be generated, and all the server is saying is you send me some response which is when concatenated with the challenge, the hash should begin with k zeros. So it doesn't matter if it is an integer or so the server is not putting any constraint on the format of that x. It can be anything, and since it's pseudo-random, so you're saying that iterating over integer is easier than string. Strings anyway will be represented in some binary format, so you can still iterate over strings also. Doesn't know the hash function, or but they have to agree upon that, because otherwise there is no hope of. Any client can do this, but he has to do a lot of work. That is the challenge. So our goal is to prevent spam, and I don't want people to send me emails too quickly. So I want to put the delay between each email the client sends me. So by making him do this hard problem, I'm just rate limiting him. So that is the, yeah. But he won't know the challenge. Hash function is known, but he won't know the challenge. So the server can pick some random thing. Yeah, but the space of challenges can be huge. Suppose I pick a 256-bit as string as a challenge, which is randomly chosen by the server. Then he can't pre-compute. It's too large a space. Somebody had a question? No, not new hash function. Hash function can be fixed. Challenge is differing. So even if the hash function is fixed to be SHA-256 always, the challenge server can pick some random challenge. Yeah. So it is able to send. So suppose 100 clients are communicating to the server. They want to send an email to the server. Then they will receive 100 different challenges. So they can send. Each of them needs to work on a different solution. Any other questions? Yes. So when this they agree upon a cryptographic service, when the client, let's say the client says that I want to send you an email, then the server says here's the challenge and K will be specified here. That you say that okay, solve this problem. It may require approximately 2 raised to K. So you give me the answer. The client can get lucky, and in the first attempt itself he can, like we saw that, the first attempt itself he may be able to find a response which satisfies that K0's constraint. So attempt, maybe I can just show the code, it may be easier. Oh, this formatting is too small. Okay, so the hash cache, you have a challenge, number of trials and zeros. So I am just, I'm going to run a loop, which is going to be number of trials times. For every time in the loop, I append the string corresponding to the integer I to the challenge. I calculate the hash y corresponding to that input x. Then I convert that y, okay, this is some Python thing. I want to convert this into binary format. Y-bin is the binary format, y in binary. And I check if y-bin starts with k zeros. Y-bin starts with 0 star num zeros. Num zeros was the, in the hash cache, the k which we are specifying. If it starts with that, then I print, okay, I found it. Otherwise, and I break out of the loop. If I doesn't start with that, then I check if the trials have been exhausted. When I is number of trials minus 1, I say not enough trials, increase the number of trials and try again. Yeah. So trials is that how many times you need to calculate this. So the client has to run a loop, and he may get lucky in the first attempt, but if he does not, he has to keep trying. But the server, when he sees the response, C concatenated to this, he has to do only one hash. So you can't overload the server by, so server, what I mean by that is that, the point is that it's an asymmetric thing. So the proof of work is difficult to generate, but it's easy to verify. The client has to generate that, but the server has to verify. The server needs to compute only the hash function only once. Any other questions about this? Yeah. But if I send the email after some time, so the client is trying to spam me. So basically, I don't trust him to follow after time t. Okay. Mm-hmm. Okay, so send email. Yeah, it may not honor it, but let's say. So the proposal was that you just tell the client you send an email after time t. So let's say I send a timestamp and say if you send me an email before that, I will do that. So suppose I create a million clients, and I said after 1 minute I'll send you an email. Then million emails will come. Yeah, yeah. No. So in this I have not put that, but okay. So you're saying that I can denial of service attack on the server by sending him wrong. Yeah. So yeah, that's possible, but those should be easier to check than generating it. So yeah, maybe that is a issue where. So then it is no different from a regular TCP denial of service attack that I just keep sending a lot of requests. So yeah, I don't even need to send a challenge. I just send. I generate a million clients and just ask for a challenge. The server will just keep sending challenges to all these clients. They will never answer, but the server is busy in sending a challenge. So yeah, maybe I'm not conveyed the whole protocol here, but anyway, let's go to maybe the reason. Maybe that is why it was not adopted. So Hashcash is not used in any real system right now. People just use machine learning to do spam filtering. Maybe the problems we are discussing are the reason it was not adopted, that in spite of this, people can still do a denial of service attack on the server. So but the idea of preventing spam in public databases, Hashcash is a proposal which did not become popular, but this has been adopted by Bitcoin to do something. We'll see. So Bitcoin mining, it's the process of adding new blocks to the blockchain. So the blockchain is a public database. People can spam it. So how do you prevent spam? You make them do some computation using hash functions. Yeah. Yeah, so I'm not sure whether it's a sent over a public channel. It will be like a point-to-point channel between the server and the client. Client will say, I want to send you an email, and then that will be sent to the server will send a challenge. But it's not like broadcast on purpose, but an eavesdropper may be able to listen to it because they don't exchange any keys or anything, so there's no encryption going on. So it is sent over, let's say, a regular internet, but anybody at the router can see that. So it's not broadcast, intentionally broadcast, but eavesdropping can happen. So you want to add new blocks to the blockchain. So the nodes which want to perform transactions will broadcast them. So what I mean by nodes which want to perform transactions, suppose I want to buy pizza using Bitcoin, then I need to transfer some amount of Bitcoin to the guy who's going to give me pizza. So I'll broadcast this transaction on the network. So there are some special nodes called miners. They will collect some of these transactions into a candidate block. So what is a candidate block? It contains a block header, number of transactions in the block, and the first transaction is special. It's called a coin-based transaction. So just bookmark this, we'll come back to this later. And then there are these regular transactions. So my transaction to buy pizza will be one of these regular transactions. And the block header again will have all these 6 fields, the version number of the block, and so far we have not looked at the other 4 fields here. This hash previous block will be the hash of the previous block. So the state of the blockchain is currently there are some blocks which are already in the blockchain, miners want to add a new block. So miners they're going to do Bitcoin mining, and that is the process by which new blocks will be added. So how do they add these? They will collect transactions which are being broadcast in the network. We'll see later what is the incentive. We'll come back to that later. So the transactions which are being broadcast on the network are one of these regular transactions. This is the and he'll create a candidate block. So this is a candidate block. It's not yet added to the blockchain. He has to do some work before he can add it. Now this hash previous block contains the double SHA-256 hash of the previous block header. Double means that you first compute the hash of the previous block header, that 80-byte header. You'll get a 256-bit output, 32 bytes. We calculate the hash of that again. So it's like f of x. So the double square of 3 will be 81. 3 square and then 9 square 81, like that. And then the hash Merkle root is going to be some hash. Finally, it is going to be like a 256-bit output. So what you do is that you take these regular transactions, the coin-based transaction, all these transactions, you lay them out in a row, and then you calculate the hash of the first transaction, hash of the second transaction. Then this is H00, H01. You concatenate the two, calculate the hash of that. And then similarly, here I have only 3 transactions. The hash of T2 is calculated as H10. This tree is not balanced, so here for H1, Okay, this is a typo. This should be. This is not a typo. Sorry. So there's no fourth transaction. So you just repeat the hash of this third transaction to balance the tree. So you concatenate H10 with H10, calculate the hash of that, you get H1. So H0 and H1, they are concatenated, and finally you get a single root hash. So such a tree is called a Merkle tree because there was a scientist called Ralph Merkle who came up with it, and this is called the Merkle root. And this is the double SHA-256 hash function. This will be a 32-byte field, 256 bits, 32-byte field. So that hash Merkle root is embedded here in the block header. The reason for that is you want your block header to depend on all the transactions, and because the hash function is collision resistant, even if I change a single bit in any of these transactions, the root hash will be different. So you want the block header to depend on all the transactions in the block, and you do that by inserting the hash Merkle root into the block header. So why do you need to do Merkle root? Why not just concatenate all these and compute the hash of that? Because hash function can take arbitrarily long strings as input. There is some advantage in this tree structure. Verification is log n, where n is the height of the tree. So there is some advantage in terms of checking whether a transaction exists in is part of a block. So that is why this tree structure. Otherwise you could have done this linear hashing also. So far the story is that a candidate block has been created by the miner, this candidate block, and this is the block header fields here. This candidate block has not yet been added to the blockchain, not yet. You have to do some work before that. So same picture as before. So this n bits field, the fifth field here, it encodes a 256-bit target value. Okay. Let's say you have a target value which begins with 16 hexadecimal zeros, that is 64 binary zeros, and all the remaining bits are 1, just for example. Now the miner who can find a nonce, so this nonce is the last field. It is a 32-byte, it's a 4-byte field. Nonce in cryptography stands for a number which is used once. The miner who can find a nonce such that the double SHA-256 hash of the block header, that is you concatenate this 4 bits, this 32 bytes, this 4 bytes, 32 bytes, 32 bytes, the remaining 12 bytes. The double SHA-256 hash of this block header should fall below the threshold or this target T. The miner who can do this can add a new block to the blockchain. So again, as we saw in Hashcash, this is 16 hexadecimal digits, so this is 64 zeros. So if I choose a single value for this nonce, the probability of success is 1 over 2 raised to 64. So in this example, a miner to be successful should have to do approximately 2 raised to 64 attempts or trials before he can find a nonce such that the double SHA-256 falls below a threshold. This picture also will give you that idea. So suppose I have these 2 raised to 256 bins, and I say start with 64 zeros. So the 64 zeros will be some initial part of some large space. So it's like you're randomly throwing balls into bins, and you want the ball to fall in some initial part of a large space. So this 2 raised to 256 is a very large number. So 64, it may be very large. Say this is the space of all outputs. Then your allowed space may be like a very small part of that. You have 256-bit hash output. You want the hash output to begin with 64 zeros. So the 2 raised to 256 minus 64. So what is that? 192, right? Yeah. So there are 2 raised to 192 possibilities. Yeah, and then there is 2 raised to 256 total possibilities. If it begins with 64 zeros, then the remaining thing can be anything. So that's why I said 2 raised to 192. The remaining bits can be anything. So in a single trial, this is the probability of success. So that's why it takes time for a miner to find such a thing. So why is mining hard? Suppose I want if the target value just starts with a single zero, in hexadecimal single zero, so 0x7 is 0111. If it starts with a single zero, then the probability of success in a single trial will be half. It is like pseudo random output, so if I just want a single zero, it's half. And if it starts with 4 binary zeros, which 1 hexadecimal digits, then it is probability of success 1 by 16. So as you keep increasing the zeros, then it becomes a very small probability. So approximately when the target value is some t, the probability of success in a single trial is t plus 1 over 2 raised to 256. When t is 0, it's 1 over 2 raised to 256, because when t is 0, there's only the all 0 value which is allowed. When the target is 256 bit value, so the maximum it can take is 2 raised to 256 minus 1, so that plus 1 divided by this we get probability 1. Say that again. That is just a, yeah. So here, you mean this encoded? Okay. So the thing is that it is not. This is so the n bits is only 4 bytes long, but this is encoding a 264 byte 256 bits target. So that's why encoding. So there is like a you can't represent every possible 256 bit value or 64 byte value, but in 4 bytes you're going to approximately cover that range. So that is why I mean, what I mean by encoding. So the n bit is only 4 bytes. There's 80 bytes. This first one is 4 bytes. These hashes are SHA-256, so there are 32 bytes each. So 32 plus 32 is 64. You remaining have only 16 bytes left. So all the other fields are 4 bytes long. That's what I mean by this encoding. Any other questions about this? So the miner who can solve this hard problem, he is allowed to add a new block. And it's a hard problem, so even if many miners are trying, one of them will succeed. And okay, so mining is hard. So why should anybody do this mining? And it's a hard problem. Why should we do that? So they get rewarded in bitcoins. So that, remember that coin-based transaction? I said the first transaction in any block. So the coin-based transaction, it creates 12.5 bitcoins in every block, and that is the only way new bitcoins can be created in the Bitcoin protocol. So this is where the currency creation using a decentralized network part comes in. So who decides how many bitcoins should be created? Can I just create an arbitrarily large number of bitcoins very quickly? You can't, because you have to solve a hard problem before you can create a block. And in each block, exactly 12.5 bitcoins are created. And each miner specifies his own address as a destination of these new coins. So the incentive for doing this hard problem of mining is that in the coin-based transaction, the miner will say, whatever new bitcoins are created, please send it to this bitcoin address. So I have not described how a bitcoin address looks like, but think of it as some string which specifies the miner's destination. And every miner is competing to solve their own proof of work puzzle. What does this mean? Every miner will put his own address. No two addresses will be the same. So the challenge, if you look at, remember that picture. So I had this block header, and this is the n nonce. This is the response part, which the miner can change. Then you had some n time, n bits, and so on. Then you had the in the third field was hash of Merkle root. The Merkle root thing. This hash Merkle root depends on all the transactions. It also depends on the coin-based transaction where the miner's address is. So if I change the miner's address, this hash will change, and this corresponds to the challenge in the Hashcash scenario, and this is the response. So each miner is trying to find a response corresponding to a different challenge. The challenges are different because the hash Merkle root is different for every miner, because hash Merkle root depends on the destination address which is there in the coin-based transaction. And why should they include those regular transactions? If they're getting rewarded in this coin-based transaction, why should they include those other regular transactions? There is a transaction fees in each of those regular transactions. So I should try to add as many regular transactions as I want if I want to maximize the transaction fees. So any questions about this? Yeah. So I'll come to that. So let me just go over the block addition workflow, and that creates a fork in the chain. So I'll come to that. I have some figures there. So the block addition workflow is as follows. So nodes will broadcast transactions. That is, I want to buy pizza with Bitcoin, so I'll broadcast a transaction. But that is an That is done by regular nodes. They don't have to be miners. The miners will accept valid transactions and reject invalid ones. By invalid ones, I mean if somebody tries to double spend some Bitcoin, that will be rejected by the miner. So it immediately solves this double spending problem. The miners have incentives to reject invalid transactions because if they create an invalid block, that is a block containing an invalid transaction, their reward will be invalid. So they always want to, yeah. Yeah, so this, let me just draw a picture here. You have this, let's say you have two candidate blocks, candidate block of miner 1 and miner 2, let's say. So here you have the block header. And we have this coin-based transaction. That is the first transaction. Then you have regular transaction 1 up to something. Then miner 2 will also have a candidate block. He'll also have a block header and regular transactions and so on. And so this coin-based transaction, so this coin-based transaction will have miner 1's address. This coin-based transaction will have miner 2's address. Now the hash of these, the Merkle root is generated from the hash of these by hashing these, the tree structure I showed you. And the Merkle root here is generated from the hash of these. The Merkle root is present in the block header. So if the miner's destination address, each miner will put his own address to receive the bitcoins. So the coin-based transactions will be different. If the coin-based transactions differ even in a single bit, because of the collision resistance property of the hash function, the Merkle roots will be different. And these Merkle roots are put in the block header, which is here. So the challenge part of that problem is the miner is solving is different. So each is solving his own proof of work puzzle. The challenge is different for every miner because the addresses are different. That is, even if you are, so the thing is that if there is even a single regular transaction which is different, they'll again be solving their, that is, they'll be solving different puzzles because the Merkle root depends on all the bits in the, of all the transaction bits in the block. Yeah, so it will be, you always append to the blockchain. Okay, so we'll see that, there's some pictures here, so that part will become clear. So the miners will accept valid transactions and reject invalid ones, so it solves the double spending right there. So the block addition workflow will look like this. So this is the solid blocks as the current state of the blockchain. And these candidate blocks, let's say there are 3 miners, they're trying to extend this block at height n-1. So there's candidate block A, B, C. Each of them is trying to solve the puzzle by trying out those nonces. And then they will compete to solve the puzzle, and as soon as they find correct response which begins with the required number of zeros, they will broadcast that solution to the network. The unsuccessful miners will abandon their current block and they will start building on the new block. So suppose this miner B succeeded, that became the block at height n. Then the other 2 miners, they'll create a candidate block A prime and C prime, and they'll start building on top of that. And miner B also will build on this. The reason for these guys to abandon their solution is that now they've already lost the race for block at height n. They don't want to lose the race for block at height n+1. So they immediately start building on top of block n. Yeah. Yeah, so that is your transaction needs to be included on the blockchain. Yes, it does.
Let's say you want to buy something like a pizza.
Yeah. Yeah. So that is right. So this is definitely a disadvantage of the Bitcoin network, that transaction confirmation it takes time. So the interblock time is designed to be 10 minutes, but it may take even days for your transaction to go through. The reason is that miners will, so each block is about, right now it is restricted to be about 4 megabytes. And miners will always include transactions which are paying the highest fees because they want to earn the highest transaction fees. So if your transaction is paying low fees, you will be deprioritized. So it may take many days before your transaction enters the blockchain. Yeah, so it can take. It's not the value, it's more like the transaction fees. So transaction fees is independent of the value in the transaction. So even if I'm transferring $1 million, if I include two smaller transaction fee, the miners will deprioritize my transaction. Yeah, so we'll see that transaction fee, how that is there. So there is something called Lightning Network, which is considered like a layer 2 on top of Bitcoin. That enables instant transactions. So that is being it's right now being developed. It's already online in the sense it's already being run on the main network, but merchant adoption is not yet there. Because if they, the thing is, suppose when miners, how is a new block propagated to the network? When a miner solves the search puzzle, he'll broadcast the solution. When I receive a new block, if I see that it has invalid transactions, then the network will reject that. Each miner will check that, and okay, that is the protocol basically. The protocol says that you should not accept transactions which are double spending or spending more than what is there in a source address. That is the part of the protocol, and as long as the majority of the network follows the protocol, it will go through.
So there should be some majority number of nodes which have accepted.
Yes, it is not in terms, we'll come to that, so it is majority in terms of hash rate, not the number of nodes. It is like how much hash power each node controls is also important. It's more like about so few hundred transactions. So the throughput is about 7 transactions per second. That is, it's like more the block size is fixed. The transaction will, the size of a transaction is a few hundred bytes. It depends on how complicated the transaction is. If you are sending to, if you are collecting money from many sources and collecting Bitcoin from many sources and sending to multiple people, so the transaction size may vary. But the size of the block, the protocol right now, initially it was only 1 megabyte, but in August last year they activated a feature which allows about 4 megabytes. So the size of the block is fixed. So miners try to push in as many high value or high transaction fee transactions as possible because they want to earn the maximum fees. Yeah. It's possible. Single block in the sense. Yeah. Yeah, so they're trying to find the block at high 10, yeah. So say it again. So since the destination addresses will be different, their puzzles will be different. So what is your question? That yeah. So the thing is that miner only cares about earning those 12.5 bitcoins. So when he calculates his candidate block, he'll make sure that the transactions in this candidate block don't double spend anything. So he's worried only about this. Each miner is selfish in the sense that he's only worried about his own gain, which is that earning those 12.5 bitcoins. So it's not about, they are not doing anything altruistic by validating transactions. They just want to make sure that the block which I create has valid transactions so that I don't lose out after doing all the hard work of mining. I don't lose out on that 12.5 bitcoins. Does that make sense? Yeah, it's possible. So these miners, they will just be listening for regular transactions. So yeah, they may differ in this also. Like it may happen that these regular transactions also will differ. The view seen by the miners, so these at each node, which is a minor node or regular node, you have something called a memory pool, which is the unconfirmed transactions which have not been included in the blockchain. So there, I may be a miner who's close to some node which sent me a very high transaction fee. Just before I started mining the next block, I heard about this high transaction fee transaction, so I'll include it. But maybe other miners did not hear about it, so they did not include it. So it's possible that the regular transactions may be different. And there's also cases where I can pay a miner out of band to prioritize my transaction. That is, I know a miner and say that, hey, I know I'm not paying a lot of fees, but I'll give you this extra money. Can you put my transaction in the next block? Hmm. So say that again. So suppose these regular transactions are different. It can also happen that these regular transactions are conflicting with these regular transactions. It can happen. They're spending the same money. Anything can happen. So one of these will win, let's say. We'll consider the case of two blocks being found at the same time in the next slide. But let's say one of these wins. Then when I construct the next block, I will check whether these transactions are conflicting with these. If they are not, then, and some of these I will construct, if some of the transactions I was trying here have already been included in this block, I will not try them in this block. I'll just create a new set of regular transactions. So if you put like 0 transaction, so right now the protocol does not allow you to send transaction with no fees, mainly to prevent spam. Because if you are not, suppose I allow 0 fees, then I can create millions of transactions where I'm paying myself. So there's no friction, 0 transaction fee, so just keep going, looping to myself. Then I can just spam the network and the network will clog. So there is something called a dust limit, that is you have to have a minimum transaction fee. But if you have a very low transaction fee and everybody else was paying higher fees, your transaction may be stuck for days and months and so on. So it did happen in December this last year, where the transaction fee in a block became larger than the Coinbase reward. Coinbase reward is 12.5 bitcoins. In December, the price of the Bitcoin hit $20,000. It was like $250,000. But everybody wanted to buy Bitcoin and they were paying very high transaction fee because they want that transaction to be included in the blockchain. So the transaction fees exceeded the block reward, which is like strange, but it did happen. No. It does have transaction fees. So it is. We'll come to that. So the right now Bitcoin, it's not like a solution which will replace credit cards. It's right now the use case is that store of value. That's it. Instead of gold, I'll store it in Bitcoin. And if I am a terrorist or something, I don't need a bank account. I can still hold value. If I'm North Korea, I can mine Bitcoin and I can hold it irrespective of US sanctions. So there is. It's a store of value. It was a decentralized payment system, and okay, media says something like no transaction fee. That's not true actually. You have to pay transaction fee. You'll see that where it is in the protocol. You'll see. Yeah. No, it is part of that. So it is the block will have all the transactions, but just that I don't want to hash the whole 4 megabytes. I'll just hash this. So when the response is, when the miner says I found a valid block, the hash of the block header should begin with a certain number of zeros. Then to verify that it begins with a certain number of zeros, I need to only hash 80 bytes. So if I have to hash 4 megabytes worth of data, it will take more time to verify that each block is correct. Hashing 80 bytes is much less. It takes much less time. Yeah, it will be stored on the blockchain. So each block will have all the transactions. It will be stored on the blockchain. So it will be broadcast. This block will be broadcast to everybody, and everybody has a copy of this blockchain. I mean, authenticate means that added to a blockchain, a block. So say that again. So where is the double spending? Suppose these two blocks have conflicting transactions, then no problem. Only one is getting included. Yeah, so what will happen is that if when I told you about this memory pool, right? Every node, miner or not, will have in RAM, it will store a set of unconfirmed transactions. So suppose I hear some transaction, before adding it to the memory pool, I'll check whether it is double spending. So I'll only include the first transaction. Let's say you have my transaction A and B. Let's say I hear transaction A first. Then when I hear transaction B, I see that it is double spending. So then I'll just not even add it to my memory pool. I'll not add it to my. That's fine. So the order of the transaction B, whatever comes in, I'll not accept the double spending one. So B comes in first into my memory pool. Then I'll reject A. So then, so that is how that part is solved. But you had a question, right? What happens in this workflow if two miners find a block at the same time? Let's say both of these found at approximately the same time, and both of them broadcast their solutions. So you have something called a fork in the chain. So you have so you have a solution from miner A and a solution from miner B. Both were found and both were broadcast. Then so both miners will broadcast. The nodes, the protocol rule is that the nodes will accept the first solution they hear and they reject the others. What I mean by first solution, this block at height n is already part of the blockchain. The block at height n plus 1, there are two solutions now. When a node hears, let's say it hears this solution, if later somebody tells it that there is another solution at height n plus 1, it will just reject that. So the picture will look like this. This is miner A, M sub A. This is miner B, that is M sub B, if you can't see it in the back. And the neighbors of miner A will think that this is the correct solution at height n plus 1. And the neighbors of miner B will think that this is the correct solution at height n plus 1. So there will be a partition in the network, logical partition in the network, where some part of the network believes that this top branch is the correct blockchain, and the other part of the network believes that this bottom branch is the correct chain. So there is something called a fork. So then what happens? So each part of the network keeps mining on top of. So this part of the network, let's say some of these are miners, they will mine on top of this, and this part of the network will mine on top of this, and it's like a random walk. Eventually one of those branches will become longer than the other. One of these branches will become longer than the other, and the protocol rule is that switch to the longest branch. If you hear, if you find out about a longer branch, just switch to it. So the nodes always switch to the longest chain they hear. So eventually it will become like this. So let's say this became longer because now miners are working on these two, trying to extend these two branches. It's a random process, so eventually one of them will become longer than the other. It's probability 0. It's not possible that both these branches will progress at equal rate. That is, they have to be found at the same time and broadcast at the same time. Eventually one will become longer than the other. Then all the nodes switch to the longest chain. Then this bottom block, which is part of the shorter chain, that will become a stale block. So two consequences: the coin-based reward here will become invalid. So the miner B cannot claim this coin-based reward later. And the transactions which were there in this block, if they were not included in the top branch, they have to be retried again. Say that again. How did?
There were two branches, right? So these transactions were confirmed according to the, as you said, to the B of the nodes.
Yeah.
So how did the nodes know that this transaction has become, these transactions are the ones which have become?
So when I hear the block at height n plus 2, then I just switch to it. Then I just I just go to the parent where both the branches had a common parent. I just go to that and just throw away everything which is.
So they have to store all the transactions from the.
Yeah, anyway they store the whole blockchain, so they know everything. It's just that when this picture is a little misleading because this part of the network only sees the top branch. It doesn't see the bottom branch. This part of the network does not see the top branch. It sees only the bottom. Now suddenly I hear about some n plus 2, then I just walk back from there until I find a parent. Then I'll just reject everything in the short.
So you have to not just keep that control, also some.
So you will store the whole blockchain, right? So you know, suppose in this case, I know that this till here both the chains were the same. So when I hear this block at n plus 2, then I say, okay, what is the parent of n plus 2? Oh, this block. I don't have this block. I should take this. And what is the parent of n plus 1? Oh, this block. Okay, now I just replace my block at height n plus 1 and n plus 2 with these blocks. So this guy will just then, whatever transactions were not included in this, I just add it back to the memory pool and retry. So this will be retried anyway. Okay. Okay, thanks. Okay, any other questions about this? So this is how the consensus, so this is called proof of work consensus. It's even if you're not interested in Bitcoin, but you're interested in enterprise blockchains, they have different consensus mechanisms. They don't have mining. Most of these enterprise blockchains which companies want to use, mining is too expensive to be part of an enterprise solution. So they have other consensus protocols. They are not based on proof of work. They're based on some other ideas. So, but we'll not cover that in this tutorial. But how often are new blocks created? So this was, what if two miners solve the puzzle at the same time? How often a new block is created? It's about approximately every 10 minutes. But how do you control that in a decentralized manner? You have this decentralized network and nodes may behave arbitrarily. How do you control that? So these two, this end time will play a role, this n bits also will play a role. So we want a block to be created every 10 minutes. Now what controls the rate of finding blocks? It is the difficulty, that is a target T, that controls the difficulty of the mining problem. So I need to keep changing that difficulty. So this target T, which controls the mining problem, is recalculated every 2016 blocks. So 2016 is the number of blocks which will be created in 2 weeks. If this 2016 is so 14 days, 24 hours per day and 6 blocks per hour. If a block was created every 10 minutes, there will be 6 blocks an hour, there are 24 hours in a day and 14 days. So 2016 is ideally the number of blocks which are created in 2 weeks if 10 minutes is the interblock time. So using this end time, it contains a timestamp of when the block was created, and this timestamp is inserted by the miner. So using this end time, you can calculate the number of seconds it took to mine the last 2016 blocks. So suppose that, and the new target is calculated according to this formula. We'll come back to this after this example. So suppose that, So suppose that 8 blocks are being created every 8 minutes. So 2016 blocks, 8 minutes and 60 seconds per minute. Suppose from this timestamps I calculated that it took approximately 8 minutes to compute to find 2016 blocks. Then the new target becomes 4 by 5 the old target. So this is the formula. T new is T sum into old target T. I'm dividing by the number of seconds in 2 weeks. 14 days, 24 hours, 60 minutes and 60 seconds. This is the number of seconds in 2 weeks. T sum is the actual time it took to find the last 2016 blocks. So I adaptively change it every 2016 blocks. So if it was that blocks will be created every 8 minutes, then the new target becomes smaller. And recall that the probability of success is proportional to the target. So if this new target becomes smaller, the probability of success in a single trial reduces, the problem becomes harder. Is that clear? So these timestamps are inserted by the miners to record what time the candidate block was created. Using those timestamps in time, I can calculate the number of seconds it took to mine the last 2016 blocks. Ideally, it should be this value. So if T sum was equal to this, the old and the new targets are the same, because on the average, blocks are being created every 10 minutes. Now if they're being created faster, I want to slow down the mining process. How do I slow down the mining process? I reduce the target, and that reduces the probability of success. So I've reduced this. But if blocks are being created too slowly, that is, let's say every 12 minutes a block is being created on the average. So it took approximately, or it took on the average 12 minutes to create the last 2016 blocks. Then when I plug in this T sum into this formula, the new target increases. So if blocks are being created every 12 minutes, I want blocks to be created faster. So I reduce the difficulty of the mining problem by increasing the target. By increasing the target T, I increase the probability of success in a single trial, so it will succeed faster. It's like that. And how is this calculated in a decentralized manner? Because everybody has a copy of the blockchain, so they know these timestamps, so everybody can do this calculation locally. Every miner will just look at the blockchain, look at the last 2016 blocks, and this is not calculated every block. It is 0 to 2015, then it was calculated, then 2015 to 4031, it was calculated, and so on. At 2015, 4031, it is a window, yeah. Yeah, so maybe I'll just rephrase your question. So if there's a transaction appears to me, how do I check its validity, that it's not double spending? So we'll see that unspent Bitcoin addresses, they are called unspent outputs. So that is maintained in the RAM. So that is, you don't have to parse the whole blockchain. So by the way, the blockchain size right now is about 200 GB. So right now if you download the Bitcoin software and you run it on your machine, it will download about 200 GB of data. So but parsing 200 GB is not inconvenient. So the unspent transactions, unspent Bitcoin addresses or places where Bitcoin has not been spent yet, that will be stored in RAM. Those are called UTXOs, unspent transaction outputs. So you just need to check that RAM data structure. Any other questions about this? So it was just a arbitrary number chosen by the creator. Just say, okay, I think it was like when I broadcast a block, it should be heard by everybody. So some kind of, I think it's an arbitrary number. It could have been 9 minutes, why not 9.5 minutes? Just a round number. I just picked it. But now it's baked into the protocol, so you can't change it. So that's now it's like it will require something called a hard fork. Okay, fine. So what? Yeah. Yeah. So about so block size is limited to about 4 megabytes, but multiple transactions. So throughput is right now about 7 transactions per second. So if you divide 10 minutes, divide the number of transactions by 10 minutes, about 6 or 7 transactions per second. So not a lot. Visa, for example, at peak time in December, around Christmas, they process about 50,000 transactions per second, some very large number. So it is not a replacement for any payment network, but it is a decentralized store of value. So it's a different use case. Corrupt in the sense? So suppose the miner allows double spend, he includes a transaction which is double spending some Bitcoin, then that block will become invalid because it contains, the protocol will say that only if he includes a double spending transaction, he loses the coin-based reward, which is huge. 12.5 Bitcoins he will not get. So why should he? Unless the double spending transaction is worth much more, then he should do. Okay, there have been transactions which transfer $400 million worth of Bitcoin. So it is possible that a miner may want to double spend, but right now the incentive is such that you just keep earning the coin-based reward. Okay, so what is the Bitcoin supply? So the currency creation rules were also one of the challenges of decentralized currencies. So the initially in 2009 when the network went live, it was 50 Bitcoins per block. And then every 210,000 blocks, that block subsidy, that 50 Bitcoins, it halves. So it became, that's about 4 years. So it became 25 in 2012 and 12.5 in 2016. So now we are in this epoch. And sometime in 2020 or maybe even 2019, it will become 6.25. So it is decreasing exponentially. So the total supply of Bitcoin, if you add up all those decreasing block rewards and assume a 10-minute block interval, it is about 21 million. So it's capped. It's a finite supply of Bitcoins. But we'll see that a Bitcoin is divisible to 10 to the 8 places. So you should not think, oh, there's only 21 million Bitcoins, but a Bitcoin is not the smallest indivisible unit. It is each Bitcoin is 10 to the 8, 100 million Satoshis. Satoshi is the smallest indivisible unit. So there's a lot of room to play with. But this graph shows the number of Bitcoins which have been mined. It is in millions. So up to in 2010 about 2 million Bitcoins were mined. Currently it's about 16.7 Bitcoins have already been mined. So only about 5 million Bitcoins are left to be mined. Yeah.
But they don't know because it is spent in some other part of the country. It is spent in both of them clashes. It should go.
So it is not a clash. We always switch to the longest chain. So we had this picture, right? So here, and we had a fork. Yeah. So when the network on the stop here, there is no double spending happening here. You may double spend here and here. Let's say I pay somebody for pizza here and with books here. But when this part of the network hears about this, it will adopt this chain, so this will become stale. No, approval means that it has to be part of the blockchain. So now this will become stale and it is no longer. So there is no. So we'll see that you should wait for a certain number of blocks to be found after the block in which your transaction is present. Suppose there is a transaction here, I should wait for some other blocks to be found after that to be confident that it will not go away in a fork. So merchants typically wait for 5 blocks after the block. So we'll wait for it. Yeah, about 1 hour. So it's like after payment, 10 minutes to find the first one and then 5 more. So it's 6 confirmations. So we'll see that. So the last Bitcoin will be mined in 2140. So this will become 6.25, then 3.125 and so on. And it will be mined in 2140. That's like a long time ahead. But even after that, transaction fees will be still an incentive for miners to mine, because each transaction is paying some transaction fees. So there is still some value in mining there. Say that again.
Because value is going
okay, but Bitcoin price can increase and take care of that. But so you're saying that if suppose the losing what value? Suppose okay, you're saying that if there is a transaction. Yeah. So the thing is, we'll see that there's something called confirmation. So if you're transferring a very large amount, then when does double spending happen? I'm getting some service or goods in return of my bitcoins, right? So I'm buying pizza or books. So if my pizza delivery guy is afraid that double spending might happen, he may wait for a few days before giving me the pizza. So if I'm transferring $400 million in return for some real estate or something, then I better wait for a few months before I give away that real estate to the person who's giving me the bitcoins. So we'll see that we'll see. So who can manipulate that? We'll see. I have some pictures later slides where I'll. How long should you wait before you consider transaction to be valid? And that will prevent this double spending problem. So we'll see that. So the payment workflow in general is like this. Merchant will share the address out of band. So I've not defined what a Bitcoin address is, but think of it like a string of bits. He'll share it out of band. That is, it is not part of the protocol. There is no concept of merchants in the Bitcoin protocol. The merchant will either send it by email or he'll show a QR code and say pay to this address. It does not use the P2P, peer-to-peer network of the Bitcoin protocol. Then the customer, he will broadcast a transaction which pays the address. So I want some service from a merchant. Merchant gives this address. Then I'll say, okay, I'm paying this address, and the transaction in which the transfer happens, I'll broadcast it onto the network. Miners will collect these broadcasted transactions into a candidate block. This thing. So you have the Coinbase transaction which rewards the miner. These are these regular transactions. So T will be part of one of these. So one of the candidate blocks containing T will be mined, eventually mined, and the merchant will wait for confirmations on T before providing goods. So confirmations is, what I mean by confirmations is that you want other blocks to be found after the current block. So suppose in this block, my transaction T, which is a regular transaction block header, it's found here. Then the merchant, when suppose this is mined, block at height n, then he sees that this corresponds to one confirmation. Then he'll wait for another block at height n plus 1 to be mined and another block. So this is one confirmation. This is 2 confirmations. So up to n plus 5. So the rule of thumb is 6 confirmations. Typically merchants wait for 6 confirmations for low value transactions. Just that the probability of the transaction going away in a fork resolution becomes small. But if I'm doing high value exchange of goods or services, then I may wait for 10 or 15 or 20 or 30, any number of. So it depends on how afraid I am of losing the money. Okay, so any questions about that? So you'll use a digital signature using a private key. So owning bitcoins is essentially owning a private key. The address is generated from the public key, and you will sign digital signature. We'll see that format. So any questions about this? So we have a tea break coming in 10 minutes, so just bear with me for another 10 minutes. So let's look at the Bitcoin transaction format. So when I'm saying these transactions are happening, what is actually happening? So what does it mean? So I have, this is the Coinbase transaction format. I have some small subheading here called pre-SegWit. So there is a feature called SegWit, it stands for segregated witness, which was activated in August. So for the purpose of this tutorial, it's not important, it is some extra feature. So let's look at the basic format. So the basic format also is allowed right now. So the Coinbase transaction, to remind you, is the first transaction in the after the number of transactions. So you have a block header, then you have a number of transactions, then the first transaction always has to be the Coinbase transaction, and it is a mandatory transaction. There can be blocks which have no regular transactions. So initially in 2009 when the network was created, nobody was using Bitcoin. So there were no regular transactions, just Satoshi was just mining his, that's running it on one machine, and there was a guy called Hal Finney, he was mining, there's only two guys on the network. They were just creating up till here Coinbase transaction, all this was not there. So it's allowed by the protocol. So this Coinbase transaction, it has something called outputs. So it can have more than one output. So I'm showing output 0 and output 1, and each output specifies two things: the amount of bitcoins in that output and something called a challenge script. Okay. And this is the second output, it has amount and challenge script. So this output format is, each of these outputs contains three fields: n value. N value is the number of satoshis locked in that output. So it is like, think of it like a deposit place. Output is a place where some bitcoins will be stored, but the value is represented in satoshis. Like I said before, one bitcoin is 100 million satoshis, and satoshi is the smallest indivisible unit. And what is this field? Again, this is a C++ variable names. N is integer. The prefix n means integer, so this is a 4-byte value. This script, the prefix script means that there is a challenge script present there. Later we'll see a response script. So Bitcoin has a scripting language for doing programmability of the money. And this pub key, this is short for public key. We'll see a reason why that is. I think I have it here. So the script pub key, the last field, it contains the challenge script, and the script pub key len, basically the byte length of the challenge script. So this is a common design pattern. Whenever you have a variable length field, script pub key is going to be the challenge script. It can have many possible lengths. When you have a variable length field, it is better to include the length of that variable length field just before the variable length field appears. Similarly here, number of transactions is included here because when the transactions is variable, it's better to include the number of transactions so that anybody who's parsing this block knows how long he should parse. So this is the Coinbase transaction format. It has only outputs. It does not have any inputs. So when this block is mined by a miner, he will specify the Coinbase transaction where he will specify the challenge script, and the challenge script is whoever can answer this challenge script can unlock these bitcoins. So when the 12.5 bitcoins are created, he will specify amounts x1 and x2 such that they add up to 12.5. Why more than one? He may be paying for electricity and cooling costs. So every time he mines a block, maybe he's paying that supplier of electricity some x2. This x1 is for himself. So he can have multiple outputs. It's not restricted to two. It can have one, but it should have at least one. It can have more than one also. This is the Coinbase transaction format. So the regular transaction is slightly more complicated. In addition to outputs, you have inputs also. So in this example, I have 3 inputs and I have 2 outputs. Again, the output format is going to be the same. So what are these inputs? So inputs have a transaction ID. So this is, let's say, a transaction with ID I1. So the input specifies the source of bitcoins. The coin-based transaction did not have inputs because the source of bitcoins was the protocol itself. They were being created by the protocol. 12.5 bitcoins are being created. But a regular transaction has to have a source of bitcoins. That source is the input. And the input is going to be, each input has a transaction ID, that is where is the source. And there's going to be a previous output, and the index of that output is specified here. So for example, transaction ID I1 and output index 0 means that the first output in transaction with ID I1. And this response script R1 is going to respond correctly to this challenge script C1. Bitcoins are stored here. To be able to spend these bitcoins, I need to provide a digital signature or provide some cryptographic response. So challenge script will specify what are the conditions under which this output can be spent. And the response script will satisfy those conditions. Or to be able to spend, it has to satisfy the conditions correctly to be able to spend the bitcoins. So we have many inputs. So each input, let's say this says transaction ID I1 and output index 1. So that means that this is the output which is being targeted. That R2 has to answer this challenge correctly. In this case, I've shown a previous regular transaction, but the previous transaction can also be a coin-based transaction. Here he had one or more inputs, which I didn't show. Here, previous coin-based transaction does not have any inputs; it has only outputs. The input is the protocol itself. So this third input, it is specifying transaction ID I2, which is the ID of this transaction, and response script output index 0. So the first output in this, there's only one output in this. And the response script R3 correctly answers the challenge C3. So it's like this. So once these R1, R2, R3 answer the challenges C1, C2, C3 correctly, this regular transaction is now allowed to spend X1 plus X2 plus X3 bitcoins. It has that many bitcoins to spend. But where is it going? This is the source. The destination is going to be specified by the outputs again, which are new challenges C4, C5, which have to be answered to spend that. So you have Y1 and Y2, amounts Y1 and Y2. So the format is, the output format is the same as before. The number of Satoshi is locked to this output. The script pub key contains the challenge script and the length of the challenge script is here. The input format now has 5 fields. The hash is the transaction ID. It is basically the double SHA-256 hash of the transaction. So you have these, anyway, it's just the transaction ID is just a double SHA-256 hash of the transaction. Since hash functions are collision resistant, as long as the transactions differ even in a single bit, transaction ID will be unique. So hash is the TX ID, N is this output index, which is 0 here. Then script sig will contain the response script. It's a variable length field, so the length of that field has to be present. N sequence is it is used for some time locking. I will not go into that here. So this is the format of a regular transaction. Okay. So hash and N identify the output being unlocked. Unlocked in the sense the response script should be provided, and script sig contains the actual response script. Okay. But what is this script? That's the next topic. But we'll just break for tea. It's almost 11:10. But any questions about this? So coin-based transaction format, then you have a regular transaction format. So one important thing is that, so there is no field for the transaction fees. So the fees are, fee is just specified by, just add the sources of bitcoins, X1 plus X2 plus X3. So this is unlocking amount X1, this is unlocking amount X2. You can't partially unlock, you have to, if you unlock, you are unlocking the whole thing. So this is unlocking X3. So this many bitcoins are allowed, are present for spending. Then you deduct the bitcoins which are going to some parties. So the remaining part is the miners to take. So if a miner includes this transaction in his block, he is rewarded with this much transaction fees. This is the number of bitcoins being unlocked, and Y1, Y2, maybe we are paying somebody for pizza or something. So these are the transaction amounts which are being sent to particular challenge scripts. The remaining bitcoins will be the transaction fee which the miner can include in his, can just claim. And the way he'll claim it is that in the coin-based transaction, this amount x3 is not 12.5 all the time. It's 12.5 plus the transaction fee of all the regular transactions in the Coinbase transaction, and all the regular transactions in the block containing this Coinbase transaction. So that's how it is. That is the actual format of the transaction. Notice that there is no invoice number, no person, or there is no identifying information. Everybody is identified by the challenge and response scripts. The challenge script identifies places where Bitcoin can be stored, and response scripts are going to be unlocking those places and sending them to new places. So it's like a flow of Bitcoin. Initially all Bitcoins will be in Coinbase transactions. Then as regular transactions take place, the Bitcoins will flow to other regular transactions. So if you have any questions, I'll take them. Otherwise, we can break for half an hour. We'll be back here at 11:40. Yes, plus transaction. Plus transaction fees. So when transaction fees were low, some miners were actually mining empty blocks which had no regular transactions. 12.5. There's no, yeah.
Bitcoin was 12.5 Bitcoins is the lowest.
The block reward or?
Yeah, lowest reward is the
Satoshis. No. Each Bitcoin is 100 million Satoshis. 10 to the 8 Satoshis. One Bitcoin is 10 to.
They were rewarded 12.5 Bitcoins.
Bitcoins, not Satoshis. 12.5 Bitcoin.
Each Bitcoin was worth some 1,000, 10,000.
Yeah, only recently it has become like that, but initially it was, yeah. Yeah, but when the protocol started, they were worthless. People bought pizza. The first transaction was somebody bought pizza for 10,000 Bitcoins. So that was like, it's, yeah, so initially it was worthless. The price of a Bitcoin was like a.
You have gold reserve. What you have here, nothing.
It's just here there is no value. It is just that perceived value. It's like anything else. It's just that in a way, if you buy shares in a company, maybe you think that the company has some fundamentals as it. So what is here? Everybody believes it's worth something, so that's why the price goes up and goes down also, like really crazy. It is being deducted from the sender. So let's say the sender is the guy who's unlocking these. So the receiver will say, I want whatever by one. If I say I'm selling one pizza for 0.1 Bitcoin, I want that 0.1 here. Yeah, he has to send. Then he has to unlock. Yeah. He has to unlock 10.1 Bitcoins. Then he can't buy anything for 10. He has to buy something for 9.999. So he can whatever he unlocks. This is what the receiver is getting, y1 plus y2. So he has to unlock enough such that he can pay the transaction fee. If he doesn't pay, it will not get broadcast on the network. Right now, zero transaction fee transactions are not allowed because you can do this self-paying spam. Just pay yourself. You have an address, recipient and the destination, sender and recipient address are the same. Just send zero transaction fee transactions to you. They are getting an incentive, but let's say now we run out of Coinbase reward in 2140. Then there's no, so you cap the Bitcoin supply. So after that, what will happen to the, what is the incentive to run a mining node? That is, transaction fee will still be an incentive. No, they can mine empty blocks also. So suppose nobody is doing any transactions in the Bitcoin network, like it was in the early days. Then they'll lose out on the transaction fees. Now they can, but if so the thing is that there's not much time I lose by including those transaction fees, then why not do it? In the sense that so it is anyway the problem is hard that there is some luck involved. Maybe you will miss out on a few milliseconds, but there is this probability that you'll win the block and also get a lot of transaction fees. No. So the mining problem is now, if you look at this, this IEEE Spectrum had a special issue on blockchain in October last year. There is a very good feature on these pictures of this mining and so on. So it is like 1 exahash is the total mining hash rate. So hashes per second. If I calculate 1 million double SHA-256, that is 1 mega hash per second. So there are mining rigs where each of them calculates about 1 gigahash per second. Then there are data centers with thousands of these mining rigs. So if you try to mine on your computer, your hash rate is so small that the probability of you winning a Bitcoin is winning a block is next to negligible. So there's no point trying. But you join something called a mining pool. That is, there's a mining pool operator. He will allow you to join, and you will collectively try to mine a single block. If you win, then the rewards are distributed according to your how many partial solutions you computed and so on. So that's possible, but if you run only your computer, then your contribution to the mining pool is negligible. So everybody just buys, many of them buy a mining rig, which costs like a few $1,000s, and they try to do mining. So I know somebody who has rented some 600 square foot place in Bangalore, and they have these mining rigs, and they're mining. But it may be just easier to just buy the Bitcoin and hope that the price rises. You may make more money than all this effort of mining and all that. So that is like a hassle. Yeah, you don't get it. You pay with regular money and get it. Yeah, so there's places called Bitcoin exchanges in India. You have Unocoin, which is a startup in Bangalore, and ZPay in Mumbai. So there you give your bank account details and you do an EFT, and then they will hold some Bitcoin for you. But that Bitcoin is held in the SQL database of the. Yeah, I checked today. It was about 9,000. Yeah. So the value is, there is some exchange rate difference. Like in India, it's about 20% more than the US prices. That's because apparently because of demand and supply. If you want, but they will quote some Indian rupees price, and you pay that. I mean, you don't need to buy a whole Bitcoin. They say you can buy even 50 rupees worth of Bitcoin, but that is not stored on the blockchain. That is stored in the SQL database. In the sense that it is not on. It's not a. But you can ask them to send it to an address. You can generate an address, and you can ask them, tell them that please send this Bitcoins to this address. Then they will take some transaction fee and send it. Then you have to hold the private key. Then you have to. Then there's a hassle of keeping the private keys safe. Yeah, you can generate as many addresses as you want. Okay, we'll break here and come back at 11:40. Formats, and there is this challenge script and response script. So let's see what is exactly in these scripts. So we need to understand this Bitcoin scripting language. It's a language which is based on another old language called Forth, which is a stack-based language. It has only 1 byte opcodes, which means that the number of possible operators is only 2 raised to 256. There's only 256, 2 raised to 8. So what is a stack-based language? So here I'll show you this is an example of Bitcoin script. You have a stack. The first operator is called op2. It just pushes the integer 2 onto the stack. So you have 2 there. Then the next operator is read. It is op3. It pushes the integer 3 onto the stack. Next operator is opadd, which pops the top 2 elements, adds them, and pushes the answer onto the stack. So the advantage of a stack-based language is that you don't need any variables. If you had to do this in C or Python, you would say I equals 2, j equals 3, I plus j. You need some variables to store your temporary values. So you, instead of that, in a stack-based language, you just use the stack to store all your variables. So it looks like assembly code. So in the actual script will be 3 bytes long. This will be a 1 byte, 1 byte, and 1 byte because it's 1 byte opcodes. But this is just a parsing of that script into a human readable format. So there will be a 3 byte script. So so I told you about this challenge and response scripts. So in general, you have an empty stack in Bitcoin, and first the response script is executed. That will populate the stack with some values x1 to xn. They will correspond to an appropriate response to this challenge script. Then the challenge script will be executed. The state of the stack will change to some yn to ym, and if the top element y1 evaluates to true, the response was correct. So that's how it will work. First response script, then challenge script. So just remember that. And empty stack state initially, response script is to populate the right response in the stack. Then the challenge script will check whether the right response has been put into the stack. Then if the top element y1 evaluates to true, then it is a response is valid. So we'll see. So let's look at an example of a challenge script. So I have this is a operator which calculates the SHA-256 hash of the top element in the stack. This 0x20 is just 32 in decimal. So it is a data push operator. So 0x20 means decimal is 32. So it just pushes the following 32 bytes onto the stack, and it is 32 bytes is 56 bits. The stack itself can contain, each element can be a byte array. So it is not that only one byte is there in a stack or only one integer. Each element in the stack can be a byte array. So these 32 bytes can be pushed onto the stack as one element. And then the op equal operator will check if the top two elements are equal. So let's see how it works. So this is a challenge script, which means it requires a response. So I have this the state of the stack as this script executes. So let's say that the response script has executed and one element x has been pushed onto the stack. So this is the challenge script starting at op hash 256. Before this, there was a data push of the value x onto the stack. Then this hash 256 will execute. It will pop the top element, remove it, compute its hash, and push the answer back onto the stack. So x will be replaced with h of x. Then this 0x20 is a data push operator. It is going to push this s. I'm representing this 32 byte or 256 bit string by s. This data push operator will push s onto the stack. Op equal is the last operator. It will check if the top two elements are equal. If they're equal, it will push 1 onto the stack. If they're not equal, it will push 0 onto the stack. If the top element is 1, the response is valid. So when is the response valid? If these two are equal. So when are these two equal? When x is the hash of x is equal to s. S was contained in the challenge script. So to unlock this challenge script, that is to provide the correct response, you have to give me an input whose hash is equal to s. And since cryptographic hash functions are difficult to invert, somebody who did not already know x will not be able to compute x from s. So it's x was used to get s. S is put in the challenge script. It says that whoever can unlock this challenge script can spend the bitcoins which are locked to that output. So he needs to know x, and just knowing s, if everybody can see the challenge script, everybody knows s because it's on the blockchain, but they won't be able to provide the right response. But this is an unsafe challenge script. Why is that? You should not use such a challenge script to lock your bitcoins. Same. Maybe not that. So what happens? Suppose I want to provide the response to this. I will have to broadcast a transaction. So how will I spend bitcoins which are locked with the challenge script? I have to broadcast a transaction which has a response script containing x. Once it's broadcast, everybody in the network knows x. Then they can change the transaction and send the money to themselves. So the way, suppose this output, this challenge script is contained in a output here. To spend from this, I have to broadcast another transaction. So this is an output. I'll have an input which will have the right response script. It will unlock this. Unlocking these means the response script will contain that x. When I broadcast this on the network, everybody in the network will know x. Then if I was sending this to buy some pizza, somebody else can just take that x and create another transaction where they may send it for some books. They'll just use the same input. So I can modify the transaction and steal these bitcoins. So that x is it is an unsafe transaction because once you broadcast on the network, everybody knows how to unlock that challenge script. So that is, should not use such a challenge script. So how do you prevent such behavior where once you broadcast a response script, nobody should be able to modify that response script and then pay somebody else of their choice. So we'll see an example of that. One safer challenge script or a better challenge script is this pay to public key. So the idea is that you use digital signatures to make this transaction is not modifiable. The reason I was able to steal bitcoins in the previous example was that this input X was being given as a response script and pizza delivery guy was the destination. I was able to modify this transaction to have the same input to unlock the same output, but some bookseller is the recipient. I'm able to modify this transaction into another transaction. When you want to protect some data from being modified, you should use digital signatures. So at a high level, a digital signature, there is a message and there is a signer who has access to a private key. He will output a tuple consisting of both the message and the signature. Then there is a verifier. He doesn't need the private key, he just needs the public key. He will take the message and signature, and using the public key, he can verify that the signature is valid for this message. He will say yes or no, the signature valid or not. And the process of going from the private key to the public key is easy, but the public key to the private key is hard. So this public key can be published, can be made public, can be published online anywhere, but nobody will be able to recover the private key from that. So signature verification can be done by any entity, but signature creation can be done only by the holder of the private key. So the pay to public key does not suffer from this problem of modification. The challenge script looks like this. So 0x21 again is 33. It's a data push operator which pushes the following 33 bytes onto the stack. This public key is going to be 33 bytes long. There is a Bitcoin uses a specific public key crypto system called elliptic curve cryptography, elliptic curve digital signature algorithm. So there the public key is 33 bytes long, and then this is a data push which pushes the data, and then there is a single operator called check sig. It's going to check a signature, digital signature, and the response script is going to be only the signature. Okay. But you might be wondering where is the message, because for a signature verification I need both the message and the signature. So we'll see where the message is coming from. So the response script will be executed first. Initially empty stack, response script followed by the challenge script. I have elided, removed the 0x21 from here. Just think of this as a data push of this public key. So initially the signature is pushed onto the stack, it's a byte array. Then the public key is pushed onto the stack, and then the check sig operator runs. It checks whether this public key or the signature corresponds to this public key, and if yes, it will return true. If no, it will return false. But where is the message coming from? The transaction itself will be the message. So this response script is contained in some input in some regular transaction which is pending from this some other previous transaction. So the transaction which contains this response itself will be the message. It will be signed. So because you don't want this message to be changed, that is the point of a digital signature. You don't want the message which is broadcast on the network to be changed by some malicious party. So you say you create a signature to verify that this message is not modified. So I'm going to show a very busy slide now. So again, it's a regular transaction with 2 inputs and 2 outputs, but I've just filled in all the fields corresponding to those inputs. So input was 5 fields each, output was 3 fields each. I just have 0, 0, 0, 0 for the first input and 1, 1, 1, 1, 1 for the second input. This bracket should end here. 0x02 is just the number of inputs, and 0x02 here is the number of inputs, the number of outputs. So this is a regular transaction. Let's say the signature is contained in the script sig. That is where the response script is there. Then the message which is used to create the signature will contain the outputs which are where the bitcoins are going. So that way, if somebody tries to modify the destination, like I did in the previous example where I was changing the pizza seller as a destination to a bookseller as a destination, I can't do that here. I can't modify this regular transaction because the message which is used to generate the signature which is present in this response contains the destinations. These output fields appear as they are. The only fields which are removed from the message are the signature fields themselves, because I can't When I'm generating the signature, I don't know what it is going to be, so I can't sign myself. I can't sign the signature itself. So those are removed. So signatures protect transactions from being modified. So simple as that. So every when a miner receives a transaction, a block which contains this transaction, he'll verify that the signature is correct. Otherwise, it will be an invalid transaction. So he won't include that. Okay, so there is a much more common format which you may have seen in if you have used Bitcoin, you may have seen this kind of like a transaction format. It's called pay to public key hash address, pay to public key. So the key thing is that you need a challenge script to receive Bitcoins, but sending a whole challenge script may be inconvenient. So you want something like a QR code so which people can send the payment to. So this pay to public key hash has this QR code feature. So it will look like some alphanumerical string like this. It always starts with a 1, that is saying that this is a P2PKH address, and it can be encoded as a QR code, and this QR code can be given by a merchant like your Paytm or any of these payment systems. The merchant can say that please pay to this QR code, which will be a pay to public key hash. So what is this alphanumeric string? It is just some base 58 encoding of a public key. So this is a public key in that elliptic curve digital signature algorithm which Bitcoin uses, and that is converted to a base 58. This is base 16, this is base 58, so that's why it's shorter. So what is base 58? You want this to be human readable and human typable without errors. So it is an alphanumeric representation of byte strings, but 0, capital O, L and I are excluded, because even in this slide if you see in this font they are looking identical. This is little l and this is capital I, they both look the same. So to prevent transcribing errors, so suppose I am typing this address, I should not make any mistakes. So small I is allowed and 0 is not here, but 0 is not, small O is allowed. This one doesn't have small O is allowed, but capital O is removed. 1 is allowed, so you don't mistake 1. You cannot mistake 1 for capital I or small l because 1 is fine. So this is the base 58 format where this is the characters and the integers. So they go from 0 to 57. Like decimal is base 10 format, so this is base 58 format. So you have a byte string and you want to, this is the byte string, you want to convert it into this base 58 format. So first you will, the thing is that when you have integers, if you convert between bases, leading zeros are eliminated. So suppose I say 0x00 AE in hexadecimal and 0x AE. As numbers these both are equal, but as byte strings they are not equal because this byte string has 2 bytes of zeros here. So you want to preserve the byte string. So leading zeros, when you are converting things into integers, you should be careful about leading zeros. So the leading zeros they encode as the leading zeros is encoded as a 1. It's an invertible encoding, so it's fine. Then you convert the resulting thing into the remaining bytes into a integer which is base 256. From base 256 you are converting it into integer because hexadecimal is 2 bytes will give you base 256. 1 byte is base 16, 1 character is base 16, 2 characters is base 256. So you convert to an integer and then that integer you convert back into a base 58 format, and each base 58 character you map it into one of these alphabets. It's doable. It may seem complicated the first time you see it, but it's doable. So that is the way you go from a byte string containing the public key to a alphanumeric representation called base 58 encoding, and this can be encoded as a QR code and so on. I think I should say, okay, so how is the encoding done? So actually it is not the public key, it is a hash of the public key. So we'll see the reason why these hashes are done. So this pay to public key address is going to be that alphanumeric string. You have a 33 byte public key. First you will apply the SHA-256 hash function. Then you will apply another hash function called RIPEMD160. You prefix an address byte, and you add a checksum of 4 bytes. The checksum is basically a double SHA-256 hash of this prefixed address, prefix hash, and you extract the first 4 bytes. Those C4 is appended at the end. The checksum is there because if you make any transcribing error, the checksum will fail. So it's an error detection scheme. And this string is, this byte string is encoded in base 58 encoding format to get this. It may seem, okay, checksum is okay, that you want to detect errors, but why is the hash being done? So why hash the public key? To see that, to go from private key to public key in elliptic cryptography, you do point addition, something called point addition. This is an easy step. To go from public key to private key, you do something, you need to solve this hard problem called the elliptic curve discrete log problem. It's quite difficult. There is no known efficient algorithm to do this. It is currently hard, but there is no future guarantee. Maybe some clever mathematician will come up with a algorithm for solving ECDLP. So to make this future proof, hashing the public key gives you this extra layer of protection. So suppose you have a pay to public key address where we saw this, there was only a public key, there was no hashing. Then by solving the ECDLP, you will get the private key. From public key, if you knew the public key, you can just solve the ECDLP and get the private key. But if you have hashes, if you have this P2PKH address, pay to public key hash address, then if I know only the address, then first of all I have to find the RIPEMD160 pre-image, because this was the second hashing which was done. Then find the SHA-256 pre-image, then solve the ECDLP. And these two are very hard problems because these both are cryptographic hash functions and they are difficult to invert. So finding a pre-image means inverting. So given a P2PKH address, I have to first invert RIPEMD160, then invert SHA-256 and then solve the ECDLP. So even if one of these hash functions is found to have a weakness, so the other one still protects it, and finally you still have to solve the ECDLP. So this is extra layer of protection which this pay to public key hash addresses provides. Any questions about this? Okay, so but how does the so what is this address and how does the response script and challenge script look like? So let's look at a transaction. So the challenge script it looks long. So basically we'll see these operators. This is a duplication operator. This is a hash 160. It just computes the hash SHA-256 and RIPEMD160 hash one after the other. This is the public key hash, and this is it checks whether the top two elements are equal, and then it checks the signature. So when I give you that alphanumeric address 1 followed by some alphanumeric characters, the public key hash address, P2PKH address, I'll first do base 58 decoding, then I'll get hash prefix byte and checksum. I'll check the checksum verifies, then I'll discard the checksum. Then I have the address prefix byte and hash. I'll throw away the address prefix and I just have the hash. So I have the hash of the public key. So I can, from the address I can recover the hash of the public key. Okay. So given if a merchant shows me a pay to PKH address, P2PKH address, then I can construct this challenge script. Okay. And the response script is going to be, it's not only contain the signature, it also needs to contain the public key. The reason is that to go from the public key hash, I can't get the public key because I have to invert two hash functions. So it's not easy. So I have to provide the response has to contain both the signature and the public key. So which means the person who is constructing the response knows what the actual public key is. So it looks like this. I'll just go over it step by step. So only 3 steps. Initially I said response script. These first 2 terms correspond to the response script that is executed. Both of them are data push operators. So signature will get pushed, then public key will get pushed. Okay. So this is the state of the stack when the challenge script is going to be starting to execute. So you first op dupe is going to duplicate the top element. So public key will be duplicated and you get another public key. Then op hash 160 will calculate the hash of the public key. That is in the next slide. So this is the calculated hash from the response script. Remember that this public key came from the response script. So this is the public key hash calculated. Then there is a pub key hash which is part of the challenge script that is pushed onto the stack. Then op equal verify will check that the calculated hash and the hash which was in the challenge script, they both are equal. If they are not equal, the script will stop executing. If it's, the reason is that if somebody is not able to provide the correct public key in the response, the execution will stop here. But if they are able to provide the first correct public key, then the calculated hash and the hash in the challenge script will be the same. Then the op equal verify will just check that they are equal, and then will just pop those two elements, so they will disappear. Then you have only these two remaining. Then op check sig will now check that the signature the signature is valid for this public key, and it will return true if it is valid and false if not. So that's how the P2PKH script execution happens. So this execution will be done by miners and even non-miner nodes who are participating in the network. Before you, when I broadcast a transaction, I'll send it to my neighbors, and then those neighbors will then broadcast it to other people. So before they broadcast a transaction, they'll verify that transaction is valid, which means in the case of this particular transaction, P2PKH transaction, they'll check that all these steps go through. If there were only miner nodes in the network and no non-miner nodes, then miner nodes are usually fewer, so you could spam those guys with a lot of invalid transactions. That is, you send a wrong signature but correct public key, then the public key hash will verify, but the signature may be wrong, but you will end up, signature verification is expensive, computationally expensive, because you have to do elliptic curve operations and those are expensive to do. So the non-miner nodes help in protecting the miners from spam, because if a non-miner node gets a transaction, then if it is wrong, then only he gets affected. But if there were no non-miner nodes, then he could easily spam the miners with invalid transactions. Okay, so there is so the Bitcoin is, okay, it's a store of value, and okay, you have these addresses where you can send and you can receive Bitcoins. Yeah. Yeah. So it's to avoid that. Yeah, you're right. It is to avoid the expensive signature checking operation. You can just by hash is easy. I mean, it's less expensive to calculate than these signature verification algorithms. So it's easy to just check that the hashes are equal. So another feature of Bitcoin, or one of the features of Bitcoin which makes it different from regular currency, is that it is a programmable kind of money. You can program the spending conditions such that the money can be spent only if certain conditions are met. As an example, let's look at a transaction which is format which is called multi-signature. Suppose you have a company and you have 3 directors in the company, but you want to ensure that funds can be spent only if 2 of the 3 sign for it. So you can do that using Bitcoin, and you can do that in Bitcoin. So you have something called M out of N multi-sig scripts. The format is that the challenge script will contain N public keys, and there's a check multi-sig operator, and the response script has to contain M signatures. So if M signatures out of the corresponding to any M out of the N public keys are presented in the response, then it's a valid M out of it's a valid M multi-sig signature script. So the M out of N that is specified here, this is an integer M and this is the integer N, and here the number of signatures will have to be exactly equal to M. So this is the challenge script, and the response has to be contain M signatures. As an example, let's consider M equals 2 and N equals 3. So the challenge script will contain 3 public keys. Let's say 3 directors create private keys and then they share the public keys. Their public keys will be part of this challenge script. To spend funds from this output which is logged by this challenge script, any 2 of the directors have to create digital signatures. So the response will look like sig1 and sig2. It can be sig2 and sig3 or sig1 and sig3, but any 2 out of the 3. There is some strange op0 here. So the thing is that there was initially when Satoshi Nakamoto released the software, this multisig was not activated. Then after a few years, after Bitcoin network was running, they said, okay, let's activate multisig. Then they found that there was a bug in the implementation which he had done, that it was popping an extra element from the stack. So in the response script, to take care of that extra popping, they had to put some dummy element here. and the thing is the Bitcoin software is that if you change the behavior, then every node in the network has to upgrade. Otherwise, there will be different behavior in different nodes. So they've just let this bug be there. Now this is part of the specification. If somebody tries to create a Bitcoin implementation, let's say in some other language like Python or even a different C++ implementation, if it doesn't have this extra dummy element, then it'll fail in the sense that it will not have consensus with the rest of the Bitcoin implementations. So you have to have bug-to-bug compatibility with the reference implementation. So bugs cannot be changed that easily. Okay, so this how the multi-stage execution. Okay, again empty stack state. Again the rule is response first, then challenge. Response consists of two signatures, just a data push. This op0 it pushes an empty array onto the stack. So empty array, then sig1 is pushed, then sig2 is pushed. So the sig2 was the last one, so it is on the top of the stack. Then this op2 will push the integer 2 onto the stack. Then the 3 public keys will get pushed, like pub key 1, 2, 3. Then op3 will push 3 onto the stack. Then the op-check multisig will read these numbers 3 and 2. First it'll read 3 and it knows that 3 public keys have to follow. Then it'll read 2 and then it knows that 2 signatures have to be provided. Then respond to 2 out of the 3 public keys. Then it will be true or false. That's how this multi-sig script operation happens. So again, this is like programmable money in the sense that okay, we can have something like this in our regular system, but we'll need somebody to implement that for us. Yeah.
Is the hash not here? Public key hash.
Okay, public key hash. Okay, so in the there is no. You're right. So there is no. Again, the public key is revealed in the clear. You're saying that why is it not here? Yeah, this is called native multisig, where the public keys are in the clear. Anybody can see them. But there is a hash version of this also. There is something called a P2SH. P2 script hash. In P2SH, if you want to protect your public keys, you want to protect the multisig using some same kind of hash as a P2K, that public key hash type. You just hash this script and you create an address. It is called P2SH. I've omitted that because of lack of time. I'll give references where you can check it out. So the P2SH addresses, they start with 3. In base 58 encoding, they start with the number 3. The P2PKH addresses, they start with 1. They always start with 1. So if you use these exchanges which you in India where you can transfer money and buy bitcoins, they'll have addresses which start with 3 because they have multi-sig. Because if the unlocking depends only on one signature, if a hacker gets hold of that one private key, then he can spend the money. So most exchanges use P2SH addresses. So there's something called P2SH multisig where all these public keys can be hidden under a hash. So there is an option, but I'm not covering that because I thought it won't fit in this presentation. But I'll provide some references at the end of this tutorial where you can go check out how this works. Any other questions about this? So it's the programmable money part which is new, and you can do this in a regular system. Let's say okay, SBI, you can ask State Bank of India, please implement multi-spending condition for me. That involves a lot of, they'll have to implement it for you, and how do you send your consent that 2 directors out of 3 directors have to spend, then maybe their physical signature or something. Here it is, the network is already running and you can easily store money in a 2 out of 3 multi-sig challenge script, and then it just works. So the programmable money part of Bitcoin is new and it's a new convenience. Okay, let's look at smart contracts. This is the last topic of this tutorial. So what are smart contracts? They're just computer protocols which enable enforcement of regular contracts. They don't eliminate trust between interacting parties, but they help minimize trust. So you can't completely have distrusting parties, but you can minimize trust between interacting parties. So I'll give you an example. Let's say I want to impose a fine for noise pollution. So we have a campus in IIT Bombay and we have a campus community hall, and there are residential buildings around that community hall. It's not like IIT-Hyderabad where the residence I notice is very close to the road and everything else will be far away. There it's quite it's a crowded place. So and they use loudspeakers. It's very cheap to rent that hall. It's less than 2,000 rupees, so people rent it all the time. And it causes a major disturbance to the residents nearby, because at 10 PM they're supposed to shut off the loudspeakers, but they never do that. But suppose we make the party organizers pay Bitcoin, security deposit in Bitcoin, saying that if you violate the noise rules, then you will lose your security deposit. Then if the noise rules are violated, we'll take the security deposit and we'll distribute it to the nearby residents because they are the affected parties. Let's say we do something like that. So how do you do this? Maybe you'll have a sensor, and after 10 PM, if the sensor records a decibel value which is higher than the allowed, then you just implement this protocol that that transaction, that Bitcoin security deposit will be paid. So this is a hypothetical example because right now you can't do this using Bitcoin. But why is this? Why does this minimize trust? Suppose I want to do this using regular money. So I have an administrative office where I ask the party organizers to pay money deposit. Then if the noise rules are violated, I have to inform that administrative office that these guys violated the noise rules. And then maybe that guy, the clerk in the admin office, is a friend of the guy who's organizing the party. He'll say, I won't. No, nothing happened or something. So then there's some trust. You need to trust the admin office to do the work for you. But in Bitcoin, if you know that the Bitcoin security, it is already, party organizers have already paid the Bitcoin, which means they have relinquished their ability to spend that Bitcoin. They've already paid it. Then you need only one person to spend that Bitcoin and distribute it to the nearby residents. But we look at an actual example. It's called escrow. We'll look at an actual example of, so this is a hypothetical example just to give you a feel for what does it mean for a smart contract to be there. In escrow, suppose Alice wants to buy a rare book from Bob. It's not a book which is available on Amazon or Flipkart. And they live in different cities, so they can't meet in person. And Bob promises to ship the book upon receiving Bitcoin payment. So he says, I want only Bitcoins. You send me a Bitcoin payment. But the problem is that Alice does not trust Bob. If Alice pays Bob, once the payment is done, if Bob does not ship the book, it will be a problem. So Alice proposes to use an escrow contract involving a third party. So escrow is a trusted party for both Alice and Bob. Let's say Carol is the escrow. Then it follows like this. First, Alice requests public keys from Bob and Carol. Alice will pay X Bitcoins to a 2 out of 3 multi-sig output. So which means that this is requires at least 2 signatures, or exactly 2 signatures. It can be any 2 from these 3. This is Alice's public key, this is Bob's public key, and this is Carol's public key. So Alice will first pay X Bitcoins to this to a multi-sig output. That means that the output is locked by this challenge script. So a response has to be provided to this challenge script to recover that or to get that X Bitcoins. So Bob ships the book once Alice's transaction is confirmed. So Bob will look in the blockchain and he'll wait for confirmations, maybe 5 confirmations, 6 confirmations. So now he's confident that the transaction will not go away in a fork resolution. These Bitcoins can be spent if any 2 out of the 3 signatures are given. So any 3 scenarios are possible, any 2 out of the 3. Alice receives the book, now and Alice is happy with the book. So Alice and Bob will sign the response script, that's sig A and sig B, to unlock this, and the money X Bitcoins will go to Bob, minus some transaction fees, because every transaction you have to pay some fees, so some transaction fees will get deducted. Second scenario, Alice receives the book, but she refuses to provide a signature for this, to unlock this. Then Bob can go and tell Carol that, see, I shipped this book to Alice, I have the proof of shipment, you help me out here. So Bob and Carol will sign, and that X Bitcoins will move from this multi-sig output to Bob. And the last scenario is Bob does not ship the book to Alice. Alice's money is stuck in this multi-sig output. Now she wants to get back the money because Bob is not sending the book, and Bob refuses to sign the refund transaction. Then Alice goes and tells Carol that this guy did not ship the book to me, can you send the money back to me? So then Alice and Carol will sign, provide the signatures, and the money will go back to Alice minus transaction fees. So Alice loses some transaction fees. Okay, this is an escrow contract which might work, but it fails if Carol colludes with Alice or Bob, because you need 2 signatures. That's one problem. So again, like I said, it does not eliminate trust, it minimizes trust. It also doesn't work if in this case Bob says I ship the book to Carol, ship the book to Alice. He shows some maybe FedEx or some speed post receipt. It may have the weight, but what's in that package is not on. He may have sent old newspapers in that. He may have sent some new book, some other book. So proof of shipment is not proof of contents. So again, this escrow contract is not perfect. So one way is to have is that you ship the book to Carol. Carol and Alice have to live in the same city. So Alice will come and check that the book is actually received and so on. Or Carol can check that the book was actually sent. So proof of shipment is not proof of contents. And this is where smart contracts, all this blockchain smart contracts, most of them fail as this example fails. The interface between the digital world and the real world is usually where they fail. In Bitcoin, you have transactions happening. Why they are happening is not recorded on the blockchain. So it's just a transfer of value, a transfer of Bitcoins from one address to the other. Here, when I'm trying to interface the real world and I'm with the digital world, this proof of shipment, not proof of contents problem happens in other scenarios also. Even in the noise pollution example, if somebody cuts the power to the sensor, which records the decibel, then the smart contract will fail. Nobody records that after 10 PM the noise was still there, or somebody puts a blanket on the sensor and muffles the noise, it will not work. So so the takeaway is that smart contracts reduce the need for trust, but they don't eliminate trust. And Bitcoin scripting language enables some smart contracts, not arbitrary smart, not powerful to express complex smart contracts. So that's all I wanted to say about smart contracts. So here are some Bitcoin learning resources. I'll be sharing these slides with the organizers, so they will send it to you. So the code is there at GitHub. This is the place. This is the C++ implementation. You can have a look at it. You can download, compile. There are even binaries available. You don't need to compile. You can just download it and run it on your machine. But you'll need about 200 GB of space. If you have an SSD, it will be much faster to the initial sync of the blockchain. This is a subreddit, Bitcoin subreddit. If you want to ask any questions, Reddit allows you to, it's a forum site if you don't know what it is. It allows you to create anonymous identities. You can ask as many identities as you want and you can ask any question you want. So there's a good place if you to see what's going on. Many of the discussions are about the price of Bitcoin. There's usually too many memes there, so but you can ask technical questions too. There's always Stack Overflow if you want to ask technical questions, like any other technical topic. Then there is also a forum called Bitcoin Talk. If you have any idea, research idea or company idea, just first check that it is not already been proposed, because most of the ideas have already been proposed. It's been existing for more than 8 years. So many of the ideas you can think of have already been proposed by somebody. So this is a good place to check for that. And you can also ask questions here. And there's also Internet Relay Chat. Some of you may not know what that is. It is like a chat room, kind of, it's like it predates your social network sites like Facebook and so on. But the developers, so the list of channels is there. There are different channels for different topics. For beginners, you can go to a certain channel, and for developers, you can go to a certain channel. You can ask any questions, and it is a real-time. You can get a real-time response. I myself have asked questions here, and some CTO for the Blockstream, which is a Bitcoin startup, he answered the question. So you get access to experts. They're just one hop away. There are a couple of books. I would recommend this first book, Princeton. It's called the Princeton book. There's a pre-publication draft at this URL. There's also YouTube videos. They have a Coursera course, and the YouTube videos are also there on this URL. It's by Arvind Narayanan and some other authors. There is a more developer-oriented book which is called Mastering Bitcoin. There's now in second edition. The first edition is available for free online. Second edition is also not very expensive. It's about 1,000 rupees, I think. But he has made the second edition more simpler. So if you want to more details, maybe the first edition is so anyway freely available. So it's a good bet. I have some notes on my web page. The feedback I've gotten is that it starts with elliptic curves, but these books don't mention elliptic curves. So this was meant more for graduate students at IIT Bombay and so on. So it is, I would not recommend it as a first reference, but this is only 150 pages long. So if you are comfortable with abstract algebra, you can just dive into this. Thanks. That's all I had. My email is there, and I have some social media links there if you want to connect with me. Thank you.
Very much. And any questions? Before we go to go, any questions? No? Okay. I want to ask one question. So now one problem is the radical change of the value of points. And so I think some people are trying to regulate them so that the trust as a point can be somehow achieved. And but again, at the same time, because the nature of the Bitcoin is distributed and the independence from some central control as a currency also. So what is your view to maintain a balance between the coordination and free behavior of points?
Okay, so the question is about liquidity in the sense, not liquidity, I say volatility. It's very volatile. Suddenly one day the price is 20,000, and then there is the price next day is 10,000. I remember there was a joke, it's like a tweet. A boy, he goes to his father and say, "Dad, I want 1 Bitcoin." Dad says, "What? You want $14,000? Why the hell do you want $20,000? What are you going to do with $9,000? So the point was that in the course of the sentence, the price is like fluctuating like crazy. So it is there is no. So the thing is that people are predicting that the price will be so high that those fluctuations will become smaller. Right now, the fluctuations are of the order of 50%. It was $20,000 in December, and now it's $9,000. And it was $6,000. So it's for regular transactions, merchants. They usually use a Bitcoin payment processor who immediately converts their money to fiat. So as long as the price does not change within an hour, it may still be used. But Bitcoin has now evolved to, it is not being used as much as a payment system, but is more being used as a store of value. The payment system, most people are reluctant to spend their Bitcoins because if they spend it today and then it rises tomorrow, then they have spent more money. So they are not using for regular payments. I think maybe Satoshi's original vision of Bitcoin as a payment system may not be fulfilled. It may become more like digital gold, where just want to store your some part of your savings in there just for the convenience. And maybe if you don't trust the government, suppose I'm a refugee, I have to leave my country. I can't carry cash easily. When I go to the country which provides me asylum, I can't carry my cash with me. But if I remember my private key, then I can just go to the new country and start my life again. Just use my private key to unlock the value which I have stored. So some kind of store of value is what where the Bitcoin is headed towards. Okay. Yeah. So other cryptocurrencies. So so what have we learned about Bitcoin? Amounts are public, which is not good in some scenarios. Somebody bought 400 million worth of Bitcoin like last month. I think this month, when the price was around $8,000, somebody put $400 million worth of US dollars. They bought that much Bitcoin. So then everybody was talking about it. So if you do high value transaction, everybody knows. Even if you do low value transaction, everybody knows. So the first thing which you want to do is confidential transactions. You want to hide the source and destination addresses, and you also want to hide the amounts. So there's one coin called Zcash, which is a fork of Bitcoin. They have opt-in confidential transactions. That is, if you want to do confidential transactions, you can do one. There's another coin called Monero, which has by default confidential transactions. So it involves some fancy digital signature algorithm called ring signatures, where the person signing the transaction is known to be one of a set of signers. So you don't know which one. And the other thing we saw in Bitcoin was that there was there's only 1 byte opcode, so only 256 opcodes. It's a very primitive language. So one would the automatic extension would be can we make a more expressive language. That's what Ethereum is doing. Ethereum has this Turing complete smart contract language, but also its attack surface is very large. It gets hacked all the time. So that is one direction. Then this. So those are some other coins which. So those are some other coins which are there. There's also this Hyperledger project, which is an enterprise blockchain project. So it's an umbrella project under Linux Foundation. So enterprises don't want any mining. They want a shared ledger which provides some kind of integrity. So Hyperledger is just an umbrella foundation, and then companies have contributed code under the Apache license, which is free of patent. So IBM has contributed Hyperledger Fabric. Intel has contributed Hyperledger Sawtooth. Then there's a Japanese technology called Hyperledger Iroha. So these things are there. So the ecosystem in Bitcoin, people are talking about confidential transactions. So they are planning to add them. There's a feature called SegWit which activated in August last year that enables new features to be introduced without requiring all nodes to upgrade. It's called a soft fork. So they managed to get that in there. So now they're talking about smart contract languages. It's in the works. I think I didn't put that here, but there is a mailing list called Bitcoin-Dev. You just search for it. So you can actually see the actual developers discussing new features, and then there is a Bitcoin improvement proposal. So if I want to add a new feature to Bitcoin, first I have to draft something called a Bitcoin improvement proposal, then present it to that Bitcoin Dev mailing list along with a reference implementation. So just ideas are not enough. Then they will vote on it and they'll discuss and modify and so on. So I don't know if that was your question. What about other coins? Did I answer partly your question? Yeah. Okay. Any other question? Yeah. Carbon, yeah. So that is a major concern. So the carbon footprint is, I think now the amount of electricity being used up is more than Singapore. It's like more than many nations. So it is quite, that has become an issue. I don't know how they will solve that. Maybe governments will say that you can use only renewable energy. Yes, Ethereum has proposed something called proof of stake, but it's not yet, I think, live. I'm not sure. Proof of stake is people who already hold Ethereum, a random group of them will be chosen and they have to sign a branch. Basically, they have to, what is the main reason for proof of work is that it allows that consensus. Miners are competing on different chains and eventually one chain becomes bigger and it becomes the main chain. So proof of stakes, it chooses one of those two. So a random group of people who already hold Ethereum have to choose between this. So proof of stake is being proposed as a more eco-friendly consensus algorithm, but there are some critics. They say that it can be attacked. It's not clear what will be the. Any other questions?
So, yeah, we can. Thank you very much.
Thanks. Thank you. Yeah. I will email you this.
Yes. Sorry. We have to handle the momentous for. Thank you very much.